Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 28th video lecture. And today we want to continue our discussion about convergence for sequence of functions, in particular ones that converge uniformly. And we're going to start off by talking about a theorem that has to do with the domains of these, emphasizes the domains of these functions for which we're having a sequence of functions defined. And we're also going to define a new metric space having to do with it's a function space. And then we're going to look at how uniform convergence helps us when we're talking about integration of a sequence of functions. Okay, let's start off with the following theorem. We're going to suppose A is a compact set, and first thing about our sequence of functions. So we have this sequence of functions, but not only are they a sequence of functions, they are continuous. On K. B, the f sub n converge pointwise to a continuous function f on K. And thirdly, we're going to assume that f sub n of x is greater than or equal to f sub n plus 1 of x. So for each x, or for every x, element of k, and n equaling 1, 2, whatever, then, what I was going to say is that for each x, the f sub n of x forms a decreasing sequence. Then, our conclusion is that the sequence f sub n's converge uniformly to f. Okay, so in essence, we can get uniform convergence if we know that the sequence is continuous on a compact set, converges pointwise, and is decreasing for each x. And we get uniform convergence. Well, we want to prove this. I made a mistake. I don't know what I wrote here. Gosh. This is the f sub n's converge pointwise to a continuous function. Gosh, I'm sorry. Okay, we won't prove this. So to prove, we're going to let or put g sub n equal to f sub n minus f. Okay. Then, what we realize is that g sub n is continuous as it is the subtraction of two continuous functions, the f sub n and f. Okay. Note for each x element k, goes to infinity of g sub n, which equals to the limit as n goes to infinity of f sub n of x minus f of x, well, that's going to be equal to 0. So what we're saying is that the g sub n's is a sequence of functions. They converge to 0 pointwise, to that function, 0. Our goal is going to be to show that the g sub n's converge to 0 uniformly. Let me write that down. We want to show that the sequence of the g sub n's converge uniformly to the function that's identically 0. Okay. Well, we let epsilon be greater than 0 be given. We let k sub n be equal to the set of all x's in k, such that g sub n of x is going to be greater than or equal to epsilon. We're going to think about this k sub n for a few seconds. Get some characteristics of it. I'm also going to let y be equal to the set of all little y's. This will be in the output space, which are complex numbers, if you will, such that, well, I shouldn't say complex numbers. These are real value functions. I didn't say that before, but these have to be real value functions because we have f sub n is greater than or equal to f sub n plus 1. You know, that characteristic yields that they're real values. So these are y's that are element of R, such that g of y, such that y is greater than or equal to epsilon. Okay. So we look at this, which is a subset of R, okay, and it is a closed subset of R, and thus the inverse image of g sub n of y is closed in k, okay, and that because that's true because g sub n is continuous. So that's one of the facts that we had about functions on metric spaces. Remember, they're continuous if their inverse image of open sets are open, but it's also true that if all inverse images of closed sets are also closed. So we get that this inverse image of this closed set is closed. But this is nothing more than, the inverse image of y is nothing more than k sub n. Let me write that down. So k sub n, which equals to this inverse of y, is closed. I'll say this is a closed subset of k. A compact set. I'll just say it this way. since K is compact, and K sub n is closed, then that gives us that K sub n is compact. Okay? Well, that just stems from facts that we've had about compact spaces. All right, next thing to observe is that since G sub n is going to be greater than or equal to G sub n plus 1 for each x, and that's true because the F sub n's have this property, the way G sub n is defined, then if x is an element of K sub n plus 1, which remember was equal to the set of all x's element K such that G of x, or G sub n, would be n plus 1 here, of x is greater than or equal to epsilon, then x is an element of K sub n, because G sub n is going to be bigger than G sub n of x is going to be greater than or equal to G sub n plus 1 of x. Which is equal to the set of all x's element K, such that G sub n of x is greater than or equal to epsilon. Okay. So what that says is that K sub n plus 1 is a subset of K sub n. Okay, well, if we fix x, an element of K, a particular x, since G sub n is a sequence of functions, converges pointwise, to 0, we see that x will not be an element of K sub n sub I, I'll say, for some n sub I big enough, large enough. This can't be in K sub n sub I, is what I should say. Because it can't always, G sub n of x can't always be greater than or equal to epsilon, because otherwise it wouldn't converge to 0. So, what this gives us is that x is not an element of the intersection of the K sub n's. And since x was arbitrary, that means that the intersection of the K sub n's is empty. Thus, by a previous theorem, and I'll write this theorem on the board, this previous theorem I'm about to write came from analysis 1. So here's the theorem I'm referring to. It's if the K sub alphas is a collection compact subsets of a metric space X such that the intersection of every finite subcollection of the case of alphas is non-empty. Okay. Then the intersection of the case of alphas is non-empty. Okay. Then that means that case of n is empty. For some n. Okay, that theorem applied to our situation means there's got to exist some case of n such that it is empty. Okay? Thus, for all n bigger than or equal to this big N, 0 is going to be less than or equal to g sub n of x, which is going to be less than epsilon, and that's true for all x element of k. So, that means that g sub n of x as a sequence of functions converges uniformly to 0. And so that implies that the sequence of f sub n converges uniformly to f. And that proves the point. Okay, next we want to give a definition. Two definitions. So the first definition, it says if X is a metric space, then this C sub X will denote the set of all complex value functions that are continuous and bounded, whose domain is X. Okay, let's say something about this metric space. Oh, well, first of all, let's say something about this C sub X, or what we did define on. So here's the definition. For each X, sorry, for each F element of this C sub x, the supremum norm of F is denoted by double bar of F and given by double bar of F, the supremum norm, is going to be equal to the sup over all x and big X of the absolute value of f of x. And we've talked about this type of norm before. We call them m sub n's. We didn't quite define it like this, but we had the supremum in a statement with a big m sub n in it. And so I'm going to refer back to that statement in just a few minutes. But as a fact, C sub x with the metric d sub c of x between g and f equal to f minus g, the supremum norm of that, is a metric space. Okay? That is this function d sub c of x, this function of c of x, defined on two elements of c sub x by this, the difference in supremum norm. That is a metric. And to prove that, I will let you look at it. So that's left to the students. And probably will be part of our last homework assignment. Okay. I'm going to state a theorem that we've really already proven in just a different form. And that is a sequence f sub n converges to f with respect to the supremum norm on C sub x. So we're thinking about this sequence being a sequence in C sub x. If and only if f sub n converges to f uniformly on x. Okay? And that is nothing more than a previous statement that we had about that m sub n being equal to the supremum between the difference of f sub n of x and f of x, all over all x's in the domain. Okay? And so this is just restating that theorem for where we're talking about C sub x. Okay? So we won't prove that. Instead, we'll prove another fact about C sub x. So that's a theorem. C sub x with the supremum norm is a complete metric space. Okay. You may have forgotten what it means to be a complete metric space. And so let me write down that definition. That is, every Cauchy sequence in C sub x converges in C sub x. Okay, that's what we got to prove. Okay. So we're going to let, well, what's in C sub x? That logics in C sub x, so to get a sequence in there, are nothing more than functions that are complex value, that are bounded and continuous. Okay? And so here, we let f sub n be a sequence, be a Cauchy sequence. In C of x. Okay? We let epsilon be greater than 0 be given. Okay? Thus, there exists a natural number exists a natural number. We'll call it n. Okay. Such that for all n and m greater than or equal to big M, well, we're talking about the Cauchy. So this norm, or the metric, or C of x, n minus m, that's going to be less than epsilon. Thus, by definition of this metric, what we have is for all m and n bigger than or equal to this capital N, the supremum over all x, the element of big X, of s of n of x minus f sub m of x will be less than epsilon. Thus, for all n and m bigger than or equal to big N, that says that f sub n of x, this should be little x's here, minus f sub m of x is x. That's going to be less than epsilon, and that's true for all x element of big X, the domain. And so, by the Cauchy criterion for uniform convergence, f sub n converge uniformly to some function, we're going to call it x, say f, on x. Now we've got to show that that f is in C of x. So, what's it mean to be in C of X? Well, you got to be continuous and other things. So, first thing is to note by previous theorem. The previous theorem is that the f sub n's to be in C of X, they were continuous. And so since they converge uniformly to f, the uniform convergence gives us that f has to be continuous. Okay? Okay. Well, now we've got to talk about another quality that we need for f to be an element of C of X, and that is f needs to be bounded. Okay? So note, since f sub n converge uniformly to f, there exists a natural number, n sub 1, a natural number, such that f sub n sub 1 of x minus f of x, that's going to be less than or equal to 1, and that's true for all x elements of big X. Thus, we're going to have that the absolute value of f sub n sub 1 of x minus the absolute value of f of x, that's going to be less than or equal to 1, okay, for all x elements of big X. Okay, so that gives us that minus 1 is going to be less than or equal to norm of f sub n sub 1 of x minus the norm of f of x, which will be less than or equal to 1. And that's true for all x element of x. And that's the property of the absolute value of real numbers. And so here's what we can say. If I want to solve for this guy, what I can say is minus 1 minus this guy is going to be less than or equal to minus the absolute value of f of x. It's going to be less than or equal to 1 minus the absolute value of f sub n sub 1 of x. And again, that's true for all x element big X. Excuse me. Okay. So that gives me that minus 1 minus f sub n sub 1 of x inside absolute values is less than or equal to minus f of x, which is less than or equal to 1 plus absolute value of f sub n sub 1 of x. And that's again true for all x element of x. Now, multiplying everything by minus 1, what we're going to get is minus 1 minus the absolute value of f sub n sub 1 of x. So that multiplying that side by minus 1, pulling it over here. is less than or equal to the absolute value of x, which is less than or equal to, well, this over here, it would be 1 plus the absolute value of f sub n, so 1 of x. And that's true again for all x element of x. Okay. So since f sub n sub 1 is an element of c of x, then f sub n sub 1 of x is bounded. So there exists an m greater than 0 such that the norm, or f, that's the value, f sub n sub 1 of x will be less than or equal to m, and that's true for all x elements of x. So what we get then is that f of x inside absolute value itself will be less than or equal to 1 plus m. And that's true for all x element of x. Thus, f of x is bounded. Thus, f is an element of c of x, and since f sub n's converge to f uniformly on x, then f sub n converges to f in c of x. So that ends the proof. I'd like to get through with one more theorem and a corollary in this lecture, and they both have to do with integration and uniform convergence. Here's the theorem. We're going to let alpha be a monotonically increasing function on a to b. We're going to suppose f sub n are Riemann Stieltjes integrable with respect to alpha on a to b. And that's true for each n equal 1, 2, forever. And suppose that the sequence of the f sub n converge uniformly to f on a to b, then f is going to be Riemann Stieltjes integral with respect to alpha, and not only that's going to happen, but that the integral from a to b of f d alpha will be equal to the limit as n goes to infinity of the interval from a to b of f sub n d alpha. And so we're pulling that limit outside that interval. See, the f is the limit as n goes to infinity of f sub n. That's what f is. It's got the limit there, and we're pulling it outside the interval. We're being able to do that. We'd like to prove this. But before we do, let me make this statement. We will consider f sub n's and f to be real value functions. Okay. Our work that we're about to present about integration of real value functions can be extended to complex value functions f equal to f sub 1 plus f sub 2I and f sub n's being equal to f sub 1 n plus f sub 2 n times I, where f sub 1, f sub 2, f sub 1 n, and f sub 2n are real values. So we're going to prove this theorem just talking about real value functions. It'll extend, okay? So we begin our proof. We're going to let alpha be a monotonically increasing function. We're going to have f sub n, a Riemann-Stieltjes integral with respect to alpha on a to b. And that's for each n. And suppose that the f sub n's converge uniformly to f on a to b. Okay. The first thing we want to do is we want to show that f is Riemann-Stieltjes integral with respect to alpha on a to b. Okay. And not only that, but as a reminder, we also want to show that that integral of f d alpha will be equal to the limit as n goes to infinity then it will beta b of f sub n beyond. We are assuming that the f sub n's are bounded because they're Riemann Stieltjes integrable, and that's the prefacing characteristic that we had for the for f to be for any function to be Riemann Stieltjes integral is that it's bounded. Okay. Thus, f is a bounded function. Since these f sub n's converge to f, and that's by similar work that we showed in the previous proof. This is convergence uniform. Okay. Thus, for each natural number n, let epsilon sub n equal to the supremum over a to b of f sub n of x minus f of x. Then, here's what we have. Then for each n, f sub n of x minus f of x inside absolute values will be less than or equal to epsilon sub n, and that's for all x element of a to b. Okay, so for each n and for all x element of a to b, we have minus epsilon n will be less than or equal to, here would be f sub n of x minus f of x, which is less than or equal to epsilon sub n. That implies that minus f sub n of x minus epsilon sub n is less than or equal to minus f of x, which is less than or equal to epsilon sub n minus f sub n of x. That implies that f sub n of x minus epsilon sub n will be less than or equal to f of x, which is less than or equal to f sub n of x plus epsilon of n. The way I got that last line is just multiply everything by minus 1. Thus, we have that the integral, the lower integral, a to b of f sub n of x minus epsilon sub n d alpha, that's going to be less than integral minus the minus integral here from a to b, the lower integral, or Riemann's integral of f of x d alpha is less than or equal to the upper integral of f of x d alpha, which is going to be less than or equal to, here we have the upper integral I want to just say the regular integral here instead of upper and lower. And here I'm going to have a to b of f sub n of x plus epsilon n d alpha. Okay. And so this is a constant. This is a constant. And so what we get is we have the integral from a to b of f sub n of x minus epsilon sub n d alpha you know, let's make these lower. Okay, this is lower and this is upper. And then I'll change this to just be the regular integral next. It's going to be less than or equal to, here, this lower integral. So I'm being a little bit very detailed, too detailed, really. Which is less than or equal to this upper integral, which is going to be less than or equal to a to b f sub n of x plus epsilon sub n d alpha. Because here I'm replacing this upper integral with this regular integral and this lower integral with this regular overall integral. And the reason I can do that is because they are the same, because the Riemann integrability of f sub n of x minus epsilon sub n and f sub n of x plus epsilon of n. Because this is Riemann integral and this is a constant making Riemann integral. And so that addition or subtraction of Riemann integral. Riemann still just integral. And so, if we look at the subtraction between the middle guys, so here's the integral from a to b minus the upper integral of f of x d alpha minus the lower integral d alpha. That's going to be less than or equal to the subtraction between these two guys. Minus the integral from a to b of f sub n of x minus epsilon sub n d alpha. Thus, we have the integral from a to b, the upper integral of f d alpha, minus the lower integral from a to b of f d alpha is less than or equal to, we have a to b of 2 times epsilon sub n d alpha. And so we get that this difference between integrals is less than, this is a constant, we can bring it out. Now I just get d alpha here. And so what that yields is that the difference between these two integrals is less than or equal to 2 times epsilon sub n. Here, this is nothing more than alpha of v minus alpha of a. I think that's what that is. Okay. Now, since the f sub n's converge uniformly, 2f on a to b, then that's going to force epsilon sub n to go to 0 as n goes to infinity. And that's true by a previous theorem we had today. So, that says that the integral from a to b, the upper, f d alpha, minus the integral from a to b of f, that's the lower integral, d alpha, that can be made as small as you want. It can be less than or equal to epsilon for any epsilon greater than 0. Thus, that says that these two intervals must be the same. And since the upper and the lower integrals are the same, thus f is Riemann-Stieltjes integral with respect to alpha. Okay. The last thing we need to do is show that the integral of f is equal to the limit of the integrals of f sub n's. Let me write that down. And so how we do that is we let epsilon be greater than 0 be given. Okay? We need a natural number n such that for all n greater than or equal to n, the absolute value between the difference of the integral from a to b of f sub n d alpha minus the integral from a to b of f d alpha, that's going to be less than epsilon. So since the integral from a to b, f sub n minus epsilon sub n d alpha is less than or equal to integral from a to b of f d alpha is less than or equal to integral from a to b of f sub n plus epsilon sub n d alpha, then that's going to force the integral from a to b of f sub n d alpha minus the integral from a to b of epsilon sub n d alpha will be less than or equal to the integral from a to b of f d alpha, which will be less than or equal to the integral from a to b of just the f sub n plus the integral from a to b of the epsilon sub n d alpha. So what we get is the integral. Well, I'll write it this way. I'll say minus epsilon sub n, as we did before, times alpha of b minus alpha of a will be less than or equal to bringing this integral over here. We have the integral a to b of f d alpha minus the integral from a to b of f sub n d alpha, which is less than or equal to, so I'm subtracting from all parts of this previous inequality the integral from a to b of f sub n d alpha. And so here I just got this integral left, but we know that's epsilon sub n times alpha b minus alpha of a. So that says that the absolute value of the integral from a to b of f d alpha minus the integral from a to b of f sub n d alpha, that's going to be less than or equal to epsilon sub n times alpha b minus alpha of a. Okay? Now, again, as we said earlier, since the limit as n goes to infinity of epsilon sub n equals to 0, there exists an n that's a natural number, so I'll say element of j, such that for all n bigger than or equal to this big N, epsilon of n inside absolute values, but it's always from greater than or equal to 0, is going to be less than or equal to whatever epsilon I want, and what I'm going to pick is the epsilon that we have over alpha b minus alpha of a. So, for all n bigger than or equal to this big N, this absolute value of a sub b of f d alpha minus the integral from a to b of f sub n d alpha, that will be less than epsilon, and that gives us that the limit as n goes to infinity of the integral from a to b of f sub n d alpha is equal to a to b of f d alpha. And that's the last thing we're going to prove. Well, I know we've gone over, but I'd like to get up a corollary that's real quick. So let's do that and we'll call it quits after this. So here's a corollary. It says if f sub n is now one of Riemann numerical functions with respect to alpha on a to b, and if f of x is equal to the sum, as n runs from 1 to infinity, f sub n of x, where we have that x is sandwiched in between a and b, with the series converging uniformly, series converging uniformly, on, I guess, a to b, then the integral from a to b of f d alpha will be equal to the sum as n runs from 1 to infinity
of the integral from a to b of f of n d alpha. Okay. So here we can pull out the sum from the integral. And so this is a consequence of what we just did, but here's how we see it. We let f sub n be Riemann-Stieltjes integral functions on a to b, and let f of x be equal to the sum as n runs from 1 to infinity of f sub n of x, where again we have the stipulation that the x is sandwiched in between a and b, and we also now consider f, I'll write down sub k of x equaling to the sum as n runs from 1 to k of f sub n of x. So that f sub k, we'll consider that, and we're going to let, because of the conditions that we're having in our theorem, in our corollary. I'm going to let we're going to let f sub k converge to f uniformly. Okay. On a to b. Okay. Well, here's the next thing to observe. It said f sub k, which is equal to the integral, which is equal to the sum of, as n runs from 1 to k of f sub n of x. Okay, is Riemann-Stieltjes integrable for each k? Since, the reason that's true is since f sub n is Riemann-Stieltjes integrable, and we're just adding up a finite number of Riemann-Stieltjes integral functions, making f sub k be Riemann-Stieltjes integral. And that's true for each k equal to 1, 2, forever. Then, by the previous theorem, f, what this converges to, is Riemann-Stieltjes integral on a to b, and the integral of f d alpha will be equal to, so it will be the limit as n goes to infinity of, well, I guess I'll say k. As k goes to infinity from a to b of f sub k of x d alpha. All right, I'll finish it up over here. Well, and that's equal to the integral, or limit, as k goes to infinity, of the integral from a to b of the sum as n runs from 1 to k of f sub n d alpha. Because you only have a finite sum, you can pull that outside of the integral. Okay. And then that's just equal to the sum as n runs from 1 to infinity of a to b of f sub n d alpha. That is the proof. Let me recap something here.
So what this correlator just told us is if you have a uniform convergence and your function f is the sum of functions. When you integrate the sum, okay, that's the same thing as integrating each term and adding them together. Okay, that's what this is saying. So you can integrate term by term to get the integral of the whole function. So that's an important fact. Thank you very much for your time and patience.